Chapter 40, File System Implementation. In this chapter, we introduce a simple file system implementation known as VSFS, the very simple file system. This file system is a simplified version of a typical Unix file system and thus serves to introduce some of the basic on-disk structures, access methods, and various policies that you will find in many file systems today. The file system is pure software. Unlike our development of CPU and memory virtualization, we will not be adding hardware features to make some aspect of the file system work better, though we will want to pay attention to the device characteristics to make sure the file system works well. Because of the great flexibility we have in building a file system, many different ones have been built, literally from AFS, the Andrew file system, to ZFS, Sun's zettabyte file system. All of these file systems have different data structures and do some things better or worse than their peers. Thus, the way we will be learning about file systems is through case studies. First, a simple file system, VSFS, in this chapter to introduce most concepts, and then a series of studies of real file systems to understand how they can differ in practice. The crux: how to implement a simple file system. How can we build a simple file system? What structures are needed on the disk? What do they need to track? How are they accessed? 40.1, the way to think. To think about file systems, we suggest thinking about two different aspects of them. If you understand both of these aspects, you probably understand how the file system basically works. The first is the data structures of the file system. In other words, what types of on-disk structures are utilized by the file system to organize its data and metadata. The first file systems we'll see, including VSFS below, employ simple structures like arrays of blocks or other objects, whereas more sophisticated file systems, like SGI's XFS, use more complicated tree-based structures. The second aspect of a file system is its access methods. How does it map the calls made by a process, such as open, read, write, etc., onto its structures? Which structures are read during the execution of a particular system call, which are written? How efficiently are all of these steps performed? If you understand the data structures and access methods of a file system, you have developed a good mental model of how it truly works, a key part of the system's mindset. Try to work on developing your mental model as we delve into our first implementation. Aside, mental models of file systems. As we've discussed before, mental models are what you are really trying to develop when learning about systems. For file systems, your mental model should eventually include answers to questions like, what on-disk structures store the file system's data and metadata? What happens when a process opens a file? Which on-disk structures are accessed during the read or write? By working on and improving your mental model, you develop an abstract understanding of what is going on instead of just trying to understand the specifics of some file system code. Though that is also useful, of course. 40.2, Overall Organization. We now develop the overall on-disk organization of the data structures of the VSFS file system. The first thing we'll need to do is divide the disk into blocks. Simple file systems use just one block size, and that's exactly what we'll do here. Let's choose a commonly used size of 4 KB. Thus, our view of the disk partition where we're building our file system is simple. A series of blocks, each of size 4 KB. The blocks are addressed from 0 to n-1 in a partition of size n 4 KB blocks. Assume we have a really small disk with just 64 blocks. Let's now think about what we need to store in these blocks to build a file system. Of course, the first thing that comes to mind is user data. In fact, most of the space in any file system is, and should be, user data. Let's call the region of the disk we use for this user data the data region. And again, for simplicity, reserve a fixed portion of the disk for these blocks, say the last 56 of 64 blocks on the disk. As we learned about last chapter, the file system has to track information about each file. This information is a key piece of metadata and tracks things like which data blocks in the data region comprise a file, the size of the file, its owner and access rights, access and modify times, and other similar kinds of information. To store this information, file systems usually have a structure called an inode. We'll read more about inodes below. To accommodate inodes, we'll need to reserve some space on the disk for them as well. Let's call this portion of the disk the inode table, which simply holds an array of on-disk nodes. Thus, our on-disk image now looks like this picture, assuming that we use 5 of our 64 blocks for inodes, denoted by eyes in the diagram. We should note here that inodes are typically not that big, for example 128 or 256 bytes. Assuming 256 bytes per inode, a 4 KB block can hold 16 inodes, and our file system above contains 80 total inodes. In our simple file system, built on tiny 64-block partitions, this number represents the maximum number of files we can have in our file system. However, do note that the same file system built on a larger disk could simply allocate a larger inode table and thus accommodate more files. Our file system thus far has data blocks D and inodes I, but a few things are still missing. One primary component that is still needed, as you might have guessed, is some way to track whether inodes or data blocks are free or allocated. Such allocation structures are thus a requisite element in any file system. Many allocation tracking methods are possible, of course. For example, we could use a free list that points to the first free block, which then points to the next free block, and so forth. We instead choose a simple and popular structure known as a bitmap, one for the data region, the data bitmap, and one for the inode table, the inode bitmap. A bitmap is a simple structure. Each bit is used to indicate whether the corresponding object/block is free, 0, or in use, 1. And thus our new on-disk layout with an inode bitmap I and a data bitmap D in lowercase. You may notice that it is a bit of overkill to use an entire 4 KB block for these bitmaps. Such a bitmap can track whether 32K objects are allocated, and yet we only have 80 inodes and 56 data blocks. However, we just use an entire 4 KB block for each of these bitmaps for simplicity. The careful reader, i.e. the reader who is still awake, may have noticed that there is one block left in the region of the on-disk structure of our very simple file system. We reserve this for the superblock, denoted by an S in the diagram below. The superblock contains information about this particular file system, including, for example, how many inodes and data blocks are in the file system, 80 and 56 respectively in this instance, where the inode table begins, block 3, and so forth. It will likely also include a magic number of some kind to identify the file system type, in this case, VSFS. Thus, when mounting a file system, the operating system will read the superblock first to initialize various parameters, and then attach the volume to the file system tree. When files with the volume are accessed, the system will thus know exactly where to look for the needed on-disk structures. 40.3. File organization, the inode. One of the most important on-disk structures of a file system is the inode. Virtually all file systems have a structure similar to this. The name inode is short for index node, the historical name given to it in Unix, and possibly earlier systems, used because these nodes were originally arranged in an array, and the array indexed into when accessing a particular inode. Aside, data structure, the inode. The inode is the generic name that is used in many file systems to describe the structure that holds the metadata for a given file, such as its length, permissions, and the location of its constituent blocks. The name goes back at least as far as Unix, and probably further back into Multics, if not earlier systems. It is short for index node, as the inode number is used to index into an array of on-disk inodes in order to find the inode of that number. As we'll see, design of the inode is one key part of file system design. Most modern systems have some kind of structure like this for every file they track, but perhaps call them different things, such as D nodes, F nodes, etc. Each inode is implicitly referred to by a number called the I number, which we've earlier called the low-level name of the file. In VSFS and other simple file systems, given an I number, you should directly be able to calculate where on the disk the corresponding inode is located. For example, take the inode table of VSFS as above, 20 KB in size, 5 4 KB blocks, and thus consisting of 80 inodes, assuming each inode is 256 bytes. Further assume that the inode region starts at 12 KB, i.e. the superblock starts at 0 KB, the inode bitmap is at address 4 KB, the data bitmap at 8 KB, and thus the inode table comes right after. In VSFS, we thus have the following layout for the beginning of the file system partition, in close-up view. To read inode number 32, the file system would first calculate the offset into the inode region, 32 times size of inode, or 8,192. Add it to the start address of the inode table on disk. Inode start address equals 12 KB. and thus arrive upon the correct byte address of the desired block of inodes, 20 KB. Recall that disks are not byte addressable, but rather consist of a large number of addressable sectors, usually 512 bytes. Thus, to fetch a block of inodes that contains inode 32, the file system would issue a read to sector 20 times 1024 divided by 512, or 40, to fetch the desired inode block. More generally, the sector address sector of the inode block can be calculated as follows. Block equals I number times size of inode T, all divided by block size. Sector equals block times block size, plus inode start address, all divided by sector size. Inside each inode is virtually all of the information you need about a file. Its type, e.g. regular file directory, etc., its size, the number of blocks allocated to it, protection information, such as who owns the file, as well as who can access it, some time information, including when the file was created, modified, or last accessed, as well as information about where its data blocks reside on disk, e.g. pointers of some kind. We refer to all such information about a file as metadata. In fact, any information inside the file system that isn't pure user data is often referred to as such. An example inode from ext2 is shown in figure 40.1. Figure 40.1, simplified ext2 inode. Size 2, name, mode. What is this inode field for? Can this file be read, written, executed? Size 2, name, UID, who owns this file? Size 4, name, size, how many bytes are in this file? Size 4, name, time, what time was this file last accessed? Size 4, name, ctime, what time was this file created? Size 4, name, mtime, what time was this file last modified? Size 4, name, dtime, what time was this inode deleted? Size 2, name, GID, which group does this file belong to? Size 2, name, links, count, how many hard links are there to this file? Size 4, name, blocks, how many blocks have been allocated to this file? Size 4, name, flags, how should ext2 use this inode? Size 4, name, OSD1, an OS dependent field. Size 60, name, block, a set of disk pointers, 15 total. Size 4, name, generation, file version used by NFS. Size 4, name, file ACL, a new permissions model beyond mode bits. Size 4, name, dear ACL, called access control lists. One of the most important decisions in the design of the inode is how it refers to where data blocks are. One simple approach would be to have one or more direct pointers, disk addresses, inside the inode. Each pointer refers to one disk block that belongs to the file. Such an approach is limited. For example, if you want to have a file that is really big, e.g. bigger than the block size multiplied by the number of direct pointers in the inode, you are out of luck. The multi-level index. To support bigger files, file system designers have had to introduce different structures within inodes. One common idea is to have a special pointer known as an indirect pointer. Instead of pointing to a block that contains user data, it points to a block that contains more pointers, each of which point to user data. Thus, an inode may have some fixed number of direct pointers, e.g. 12, and a single indirect pointer. If a file grows large enough, an indirect block is allocated from the data block region of the disk, and the inode slot for an indirect pointer is set to it. Assuming 4 KB blocks and 4 byte disk addresses, that adds another 1024 pointers. The file can grow to be 12 plus 1024 times 4K, or 4144 KB. Tip: consider extent-based approaches. A different approach is to use extents instead of pointers. An extent is simply a disk pointer plus a length in blocks. Thus, instead of requiring a pointer for every block of a file, all one needs is a pointer and a length to specify the on-disk location of a file. Just a single extent is limiting, as one may have trouble finding a contiguous chunk of on-disk free space when allocating a file. Thus, extent-based file systems often allow for more than one extent, thus giving more freedom to the file system during file allocation. In comparing the two approaches, pointer-based approaches are the most flexible but use a large amount of metadata per file, particularly for large files. Extent-based approaches are less flexible but more compact. In particular, they work well when there is enough free space on the disk and files can be laid out contiguously, which is the goal for virtually any file allocation policy anyhow. Now back to the pointer approach. Not surprisingly, in such an approach, you might want to support even larger files. To do so, just add another pointer to the inode, the double indirect pointer. This pointer refers to a block that contains pointers to indirect blocks, each of which contain pointers to data blocks. A double indirect block thus adds the possibility to grow files within an additional 1024 times 1024, or 1,000,000 4 KB blocks. In other words, supporting files that are over 4 GB in size. You may want even more though, and we bet you know where this is headed. The triple indirect pointer. Overall, this imbalanced tree is referred to as the multi-level index approach to pointing to file blocks. Let's examine an example with 12 direct pointers as well as both a single and double indirect block. Assuming a block size of 4 KB and 4 byte pointers, this structure can accommodate a file of just over 4 GB in size, i.e. 12 plus 1024 plus 1024 squared times 4 KB. Can you figure out how big of a file can be handled with the addition of a triple indirect block? Hint, pretty big. Many file systems use a multi-level index, including commonly used file systems such as Linux and ext3, NetApp's WAFL, as well as the original Unix file system. Other file systems, including SGI, XFS, and Linux ext4, use extents instead of simple pointers. See the earlier aside for details on how extent-based schemes work. They are akin to segments in the discussion of virtual memory. You might be wondering, why use an imbalanced tree like this? Why not a different approach? Well, as it turns out, many researchers have studied file systems and how they are used, and virtually every time they find certain truths that hold across the decades. One such finding is that most files are small. This imbalanced design reflects such reality. If most files are indeed small, it makes sense to optimize for this case. Thus, with a small number of direct pointers, 12 is a typical number, an inode can directly point to 48 KB of data, needing one or more indirect blocks for larger files. See Agrawal et al. For a recent-ish study. Figure 40.2 summarizes those results. Most files are small. About 2K is the most common size. Average file size is growing. Almost 200K is the average. Most bytes are stored in large files. A few big files use most of the space. File systems contain lots of files, almost 100K on average. File systems are roughly half full. Even as disks grow, file systems remain about 50% full. Directories are typically small. Many have few entries. Most have 20 or fewer. Of course, in the space of inode design, many other possibilities exist. After all, the inode is just a data structure, and any data structure that stores the relevant information and can query it effectively is sufficient. As file system software is readily changed, you should be willing to explore different designs should workloads or technologies change. 40.4 Directory Organization. In VSFS, as in many file systems, directories have a simple organization. A directory basically just contains a list of entry name, inode number pairs. For each file or directory in a given directory, there is a string and a number in the data blocks of the directory. For each string, there may also be a length, assuming variable size names. For example, assume a directory dir, inode number 5, has 3 files in it, foo, bar, and foobar is a pretty long name, with inode numbers 12, 13, and 24 respectively. The on-disk data for dir might look like inum 5 reclen 12 strlen 2 name dot, inum 2 reclen 12 strlen 3 name dot dot, inum 12 reclen 12 strlen 4 name foo, inum 13 reclen 12 strlen 4 name bar, inum 24 reclen 36 strlen 28 name foobar is a pretty long name. In this example, each entry has an inode number, record length, the total bytes for the name plus any leftover space, string length, the actual length of the name, and finally the name of the entry. Note that each directory has two extra entries, dot and dot dot. The dot directory is just the current directory, in this example, dir, whereas dot dot is the parent directory, in this case, the root. Deleting a file, e.g. calling unlink, can leave an empty space in the middle of the directory, and hence there should be some way to mark that as well, e.g. within a reserved inode number such as 0. Such delete is the reason why record length is used. A new entry may reuse an old, bigger entry and thus have extra space within. Aside, linked-based approaches. Another simpler approach in designing inodes is to use a linked list. Thus, inside an inode, instead of having multiple pointers, you just need one, to point to the first block of the file. To handle larger files, add another pointer at the end of that data block, and so on, and thus you can support large files. As you might have guessed, the linked file allocation performs poorly for some workloads. Think about reading the last block of a file, for example, or just doing some random access. Thus, to make the linked allocation work better, some systems will keep an in-memory table of link information. Instead of storing the next pointers with the data blocks themselves, the table is indexed by the address of data block D. The content of an entry is simply D's next pointer, i.e. the address of the next block in a file which follows D. A null value could be there too, indicating an end of file, or some other marker to indicate that particular block is free. Having such a table of next pointers makes it so that a linked allocation scheme can effectively do random file access simply by first scanning through the in-memory table to find the desired block and then accessing on disk it directly. Does such a table sound familiar? What we have described is the basic structure of what is known as the file allocation table, or FAT file system. Yes, this classic old Windows file system before NTFS is based on a simple linked-based allocation scheme. There are other differences from a standard Unix file system too. For example, there are no inodes per se, but rather directory entries which store metadata about a file and refer directly to the first block of said file, which makes creating hard links impossible. Now, you might be wondering exactly where directories are stored. Often, file systems treat directories as a special type of file. Thus, a directory has an inode somewhere in the inode table, with the type field of inode being marked as directory instead of regular file. The directory has data blocks pointed to by the inode and perhaps indirect blocks. These data blocks live in the data block region of our simple file system. Our on-disk structure thus remains unchanged. We should also note again that this simple linear list of directory entries is not the only way to store such information. As before, any data structure is possible. For example, XFS stores directories in B-tree form, making file create operations which have to ensure that a file name has not been used before creating it, faster than systems with simple lists that must be scanned in their entirety. Aside, free space management. There are many ways to manage free space. Bitmaps are just one way. Some early file systems use free lists, where a single pointer in the superblock was used to point to the first free block. Inside that block, the next free pointer was kept, thus forming a list through the free blocks of the system. When a block was needed, the head block was used and the list updated accordingly. Modern file systems use more sophisticated data structures. For example, SGI's XFS uses some form of a B-tree to compactly represent which chunks of the disk are free. As with any data structure, different time-space trade-offs are possible. 40.5 Free Space Management. A file system must track which inodes and data blocks are free and which are not, so that when a new file or directory is allocated, it can find space for it. Thus, free space management is important for all file systems. In VSFS, we have two simple bit masks for this task. For example, when we create a file, we will have to allocate an inode for that file. The file system will thus search through the bitmap for an inode that is free and allocate it to the file. The file system will have to mark that inode as used with a 1 and eventually update the on-disk bitmap with the correct information. A similar set of activities take place when a data block is allocated. Some other considerations might also come into play when allocating data blocks for a new file. For example, some Linux file systems such as ext2 and ext3 will look for a sequence of blocks, say 8, that are free when a new file is created and needs data blocks, by finding such a sequence of free blocks and then allocating them to the newly created file. The file system guarantees that a portion of the file will be contiguous on the disk, thus improving performance. Such a pre-allocation policy is thus a commonly used heuristic when allocating space for data blocks. 40.6 Access Paths, Reading and Writing. Now that we have some idea of how files and directories are stored on disk, we should be able to follow the flow of operation during the activity of reading or writing to a file. Understanding what happens on this access path is thus the second key in developing an understanding of how a file system works. Pay attention. For the following examples, let us assume that the file system has been mounted and thus the superblock is already in memory. Everything else, i.e. inodes directories, is still on the disk. Reading a file from disk. In this simple example, let us first assume that you want to simply open a file, e.g. /foo/bar, read it, and then close it. For this simple example, let's assume the file is just 12 KB in size, i.e. 3 blocks. When you issue an open /foo/bar, o read-only call, the file system first needs to find the inode for the file bar to obtain some basic information about the file, permissions information, file size, etc. To do so, the file system must be able to find the inode, but all it has right now is the full path name. The file system must traverse the path name and thus locate the desired inode. All traversals begin at the root of the file system in the root directory, which is simply called /. Thus, the first thing the FS will read from disk is the inode of the root directory, but where is this inode? To find an inode, we must know its I number. Usually, we find the I number of a file or directory in its parent directory. The root has no parent by definition. Thus, the root inode number must be well known. The FS must know what it is when the file system is mounted. In most Unix file systems, the root inode number is 2. Thus, to begin the process, the FS reads in the block that contains inode number 2, the first inode block. Once the inode is read in, the FS can look inside of it to find pointers to data blocks, which contain the contents of the root directory. The FS will thus use these on-disk pointers to read through the directory, in this case looking for an entry for foo. By reading in one or more directory data blocks, it will find the entry for foo. Once found, the FS will also have found the inode number of foo. Say it is 44, which is what it will need next. The next step is to recursively traverse the path name until the desired inode is found. In this example, the FS reads the block containing the inside of foo, the inode of foo, and then its directory data, finally finding the inode number of bar. The final step of open is to read bar's inode number into memory. The FS then does a final permissions check, allocates a file descriptor for this process in the per process open file table, and returns it to the user. Once open, the program can then issue a read system call to read from the file. The first read at 0 offset, unless lseek has been called, will thus read in the first block of the file, consulting the inode to find the location of such a block. It may also update the inode with a new last access time. The read will further update the in-memory open file table for this file descriptor, updating the file offset such that the next read will read at the second file block, etc. At some point, the file will be closed. There is much less work to be done here. Clearly, the file descriptor should be deallocated, but for now, that is all the file system really needs to do. No disk IOs take place. A depiction of this entire process is found in figure 40.3. Time increases downward in the figure. In the figure, the open causes numerous reads to take place in order to finally locate the inode of the file. Afterwards, reading each block requires the file system to first consult the inode, then read the block, and then update the inode's last access time field with a write. Spend some time and understand what is going on. Also note that the amount of I/O generated by the open is proportional to the length of the path name. For each additional directory in the path, we have to read its inode as well as its data. Making this worse would be the presence of large directories. Here, we only have to read one block to get the contents of a directory, whereas with a large directory, we might have to read many data blocks to find the desired entry. Yes, life can get pretty bad when reading a file, as you're about to find out. Writing to a file, and especially creating a new one, is even worse. Writing a file to disk. Writing to a file is a similar process. First, the file must be opened, as above. Then the application can issue write calls to update the file with new contents. Finally, the file is closed. Unlike reading, writing to the file may also allocate a block unless the block is being overwritten, for example. When writing out a new file, each write not only has to write data to disk, but has to first decide which block to allocate to the file and thus update other structures of the disk accordingly, e.g. the data bitmap and inode. Thus, each write to a file logically generates 5 IOs, one to read the data bitmap, which is then updated to mark the newly allocated block as used, one to write the bitmap to reflect its new state to disk, 2 more to read and then write the inode, which is updated with the new block's location, and finally, 1 to write the actual block itself. The amount of write traffic is even worse when one considers a simple and common operation such as file creation. To create a file, the file system must not only allocate an inode, but also allocate space within the directory containing the new file. The total amount of I/O traffic to do so is quite high. 1 read to the inode bitmap to find a free inode, 1 write to the inode bitmap to mark it allocated, 1 write to the new inode itself to initialize it, 1 to the data of the directory to link the high-level name of the file to its inode number, and 1 read and write to the directory inode to update it. If the directory needs to grow to accommodate the new entry, additional IOs, i.e. to the data bitmap and the new directory block, will be needed too. All that just to create a file. Let's look at a specific example where the file /foo/bar is created and 3 blocks are written to it. Figure 40.4 shows what happens when during the open, which creates the file, and during each of these 4 KB writes. In the figure, reads and writes to the disk are grouped under which system call caused them to occur, and the rough ordering they might take place in goes from top to bottom of the figure. You can see how much work it is to create the file. 10 IOs in this case, to walk the path name and then finally create the file. You can also see that allocating write costs 5 IOs, a pair to read and update the inode, another pair to read and update the data bitmap, and then finally the write of the data itself. How can a file system accomplish any of this with reasonable efficiency? The crux: how to reduce file system I/O costs. Even the simplest of operations like opening, reading, or writing a file incurs a huge number of I/O operations scattered over the disk. What can a file system do to reduce the high costs of doing so many IOs? 40.7. Caching and buffering. As the examples above show, reading and writing files can be expensive, incurring many IOs to the slow disk. To remedy what would clearly be a huge performance problem, most file systems aggressively use system memory, DRAM, to cache important blocks. Imagine the open example above. Without caching, every file open would require at least 2 reads for every level in the directory hierarchy, 1 to read the inode of the directory in question, and at least 1 to read its data. With a long path name, e.g. /1, /2, /3, /../100, /file.txt, the file system would literally perform hundreds of reads just to open the file. Early file systems thus introduced a fixed size cache to hold popular blocks. As in our discussion of virtual memory, strategies such as LRU and different variants would decide which blocks to keep in cache. This fixed size cache would usually be allocated at boot time to roughly 10% of total memory. This static partitioning of memory, however, can be wasteful. What if the file system doesn't need 10% of memory at a given point in time? With the fixed size approach described above, unused pages in the file cache cannot be repurposed for some other use and thus go to waste. Modern systems, in contrast, employ a dynamic partitioning approach. Specifically, many modern operating systems integrate virtual memory pages and file system pages into a unified page cache. In this way, memory can be allocated more flexibly across virtual memory and file system, depending on which needs more memory at a given time. Now imagine the file open example with caching. The first open may generate a lot of I/O traffic to read in directory inode and data, but subsequent file opens of that same file or files in that same directory will mostly hit in the cache, and thus no I/O is needed. Tip: understanding static versus dynamic partitioning. When dividing a resource among different clients or users, you can use either static partitioning or dynamic partitioning. The static approach simply divides the resource into fixed proportions once. For example, if there are 2 possible users of memory, you can give some fixed fraction of memory to one user and the rest to the other. The dynamic approach is more flexible, giving out different amounts of the resource over time. For example, one user may get a higher percentage of disk bandwidth for a period of time, but then later the system may switch and decide to give a different user a larger fraction of available disk bandwidth. Each approach has its advantages. Static partitioning ensures each user receives some share of the resource, usually delivers more predictable performance, and is often easier to implement. Dynamic partitioning can achieve better utilization by letting resource-hungry users consume otherwise idle resources, but can be more complex to implement, and can lead to worse performance for users whose idle resources get consumed by others and then take a long time to reclaim when needed. As is often the case, there is no best method. Rather, you should think about the problem at hand and decide which approach is most suitable. Indeed, shouldn't you always be doing that? Let us also consider the effect of caching on writes. Whereas read I/O can be avoided altogether with a sufficiently large cache, write traffic has to go to disk in order to become persistent. Thus, a cache does not serve as the same kind of filter on write traffic that it does for reads. That said, write buffering, as it is sometimes called, certainly has a number of performance benefits. First, by delaying writes, the file system can batch some updates into a smaller set of I/Os. For example, if an inode bitmap is updated when one file is created and then updated moments later as another file is created, the file system saves an I/O by delaying the write after the first update. Second, by buffering a number of writes in memory, the system can then schedule the subsequent I/Os and thus increase performance. Finally, some writes are avoided altogether by delaying them. For example, if an application creates a file and then deletes it, delaying the write to reflect the file creation to disk avoids them entirely. In this case, laziness in writing blocks to disk is a virtue. For the reasons above, most modern file systems buffer writes in memory for anywhere between 5 and 30 seconds, representing yet another trade-off. If the system crashes before the updates have been propagated to disk, the updates are lost. However, by keeping writes in memory longer, performance can be improved by batching, scheduling, and even avoiding writes. Tip: understand the durability/performance trade-off. Storage systems often present a durability/performance trade-off to users. If the user wishes data that is written to be immediately durable, the system must go through the full effort of committing the newly written data to disk, and thus the write is slow but safe. However, if the user can tolerate the loss of a little data, the system can buffer writes in memory for some time and write them later to the disk in the background. Doing so makes writes appear to complete quickly, thus improving perceived performance. However, if a crash occurs, writes not yet committed to disk will be lost, and hence the trade-off. To understand how to make this trade-off properly, it is best to understand what the application using the storage system requires. For example, while it may be tolerable to lose the last few images downloaded by your web browser, losing part of a database transaction that is adding money to your bank account may be less tolerable. Unless you're rich, of course. In that case, why do you care so much about hoarding every last penny? Some applications, such as databases, don't enjoy this trade-off. Thus, to avoid unexpected data loss due to write buffering, they simply force writes to disk by calling fsync, by using direct I/O interfaces that work around the cache, or by using the raw disk interface and avoiding the file system altogether. While most applications live with the trade-offs made by the file system, there are enough controls in place to get the system to do what you want it to, should the default not be satisfying. 40.8 Summary. We have seen the basic machinery required in building a file system. There needs to be some information about each file, metadata, usually stored in a structure called an inode. Directories are just a specific type of file that store name, inode number mappings. And other structures are needed too. For example, file systems often use a structure such as a bitmap to track which inodes or data blocks are free or allocated. The terrific aspect of file system design is its freedom. The file systems we explore in the coming chapters each take advantages of this freedom to optimize some aspect of the file system. There are also clearly many policy decisions which we have left unexplored. For example, when a new file is created, where should it be placed on disk? This policy and others will also be the subject of future chapters. Or will they? Cue mysterious music that gets you even more intrigued about the topic of file systems.